Now let's talk about semantic segmentation. The task is to assign one label to each pixel, and usually the label indicates the semantic meaning of that underlying object. For example, in this image, we want to assign all the pixels of a car to the car label, and assign all the pixels of the road to the same label. And please note that here in semantic segmentation, we do not care about identity. It means that when we assign the car label to different pixels, we only worry about their category. We do not care that whether this pixel and this pixel belong to the same car. And there a key question of using convolutional networks for semantic segmentation or even other more complicated tasks. That is, how we can go from one label per image to one per pixel. So in convolutional networks for classification, we will aggressively downsample the image so that we will squeeze the whole image or downsample the image into one pixel. And that will lose a lot of spatial information, and is undesirable for semantic segmentation and even other tasks like object detection. So there, in the early years, people make a lot of attempts to increase the resolution of the convolutional networks, and the goal here is to use the networks or use the weights learned from large-scale image classification dataset like ImageNet. Use those information as initialization for the representation of the other tasks, so that we can directly reuse those filters on a different task, and probably do slightly fine-tuning in order to build a good representation for a different task. And the most significant, the idea for semantic segmentation started with fully convolutional networks. The observation here is for classification, we first take a object-centric image and then pass it into a network that aggressively downsample the image into one pixel, and then we get a probability distribution for that for the possible categories of that image. And then if we want to segment the image, or we want to make prediction for a full resolution image, we can densely apply the same network on the image. So here, because the convolutional networks are of course using convolution, and is spatially for each convolutional kernel is spatially invariant, and therefore the same kernel work on a smaller area of image can easily be extended to the whole image. And the only side effect is we can have high resolution output for the convolution kernels. And as you can see now, we are still downsample the image multiple times, but because the initial resolution is higher, and because we are having higher activation map or higher output resolution for each layer, we can actually have a label map output for the whole image, although it has been significantly downsampled. Usually this downsample ratio is 32. And as you can see here, so if we directly apply the convolution, the learned filter from ImageNet or from image classification on this segmentation on this high resolution image, then we can get a prediction like this, and it gives us a low lower resolution prediction, we can do interpolation like binary upsampling to get a full resolution output. And after we get the downsampled feature map, we can fuse it. With a lower level layer, so that the lower level layer has higher resolution, but probably weak specular meaning because it is a shallower layer. But when we combine them together, we can get higher resolution, but at the same time we can get information at a deep level, and we can keep doing this upsampling. Say we have this resolution, and we can combine it with an even shallower layer to learn to get a higher resolution, learn to combine these two layers so that we can have higher resolution at the same time more semantic information. And you can see this scheme indeed can increase the resolution of the output, and we can get a more and more clear prediction for the output segmentation map. And this scheme has also been invented in some other concurrent work with fully convolutional networks. For example, this network called UNet, which is designed for biomedical image segmentation, and it uses a similar idea. We will first use consecutive convolution blocks to learn the filter from high resolution image, and at the same time gradually downsample the image to a lower resolution, so that we can learn the deeper representation for the image. At the same time, use relatively small filters. Like here, we can keep reusing the 3x3 convolution, but at the same time, in the middle layer, the filter can have very big receptive field relative on the original input image, although we have been using 3x3 convolutions. And then we can use the upsampling scheme proposed by fully convolutional networks to gradually merge the deep representation with shallow layers which have high resolution, to increase the resolution gradually until we get desired upsampled resolution. And this scheme has also been pushed into a further extension. For example, why do we stop at 2 times upsampling, like in fully convolutional network? Why don't we keep upsampling until we have a much higher resolution output directly? So here I want to mention that in fully convolutional network, they only upsample the output resolution, so that the output is downsample the input by 8 times, or by ratio of 8, not 8 times. And then we can do a binary upsampling to upsample the output image. And in this segment, they learn to upsample the feature map or the prediction to the original resolution. And similar designs has been used in a lot of different works. Like basically, those network models follow this hourglass shape. They will first downsample the image, so that we can use 3x3 convolution at each level while achieving much bigger receptive field. And then after we get this deep representation, which consider a big receptive field, which means that they are considering big context, then they have a very strong semantic information. We can combine those deep representation with lower layers and gradually upsample the outputs to the full resolution, eventually to achieve 1 label per pixel. and we can even connect those output of those networks with a learned CRF, which is conditional random field. So here we can convert this conditional random field into a neural network and do a joint optimization, so that we can get a better, we can get finer output of the network. However, this doesn't resolve all the problems. And usually from the output of FCN, we usually observe um, very blurred um, outcome, so that we do not usually see the boundaries of the objects very clearly. And here, let's see what's actually happening there. So for fully convolutional network, originally we have a classification network, and it aimed to downsample the image into one label. And with fully convolutional network, we operate this network, we operate the same network, same set of filters on higher resolution image to gradually get a higher, deep representation. And then we have very high, like deep network, which has strong semantic information, and we have lower layers which has higher spatial information but weaker semantic information. The goal here is we want to upsample the semantic information with and combine it with spatial information so that we can get the best of both worlds. However, that's sometimes do not work very well, and we constantly observe inaccurate boundaries from the output. For example, when we want to segment those chairs, you can see that we do not observe the back of the chair clearly from the output image. And what's worse, so it usually miss some small objects or thin parts from the original image. Like here, the output segmentation map for those chairs do not depict the existence of the chair legs, not even mentioning the boundaries of those legs. And let's take a step back and think about what will why does what will be the ideal network for semantic segmentation, so that we can understand why those blurred boundary, and the missing parts can happen. So first of all, in an ideal world, when we want to assign one label for each pixel in the image, we actually do not want to squeeze the resolution because we want to keep the output resolution. We hope that the spatial information can pass successfully from input to the output. And then the question here is how we can transform the representation and learned by the classification network to the ideal case, like which means that we do not lose the spatial information. And here we introduce the dilated convolution. So it's actually a simple generalization of the normal convolution. For example, this is a cartoonish representation of a symmetric convolution on one input image. And this is one operation of the kernel. Basically, we will apply the kernel into these 9 pixels and multiply each location with the kernel weight and then sum them together. So in dilated convolution, instead of tap each adjacent pixel, we can tap the other pixel or every third pixel. We are no longer constrained to typing to adjacent pixel, and we define the distance between the adjacent typing, the dilation. So by this definition, in the original convolution, the dilation is 1, means that the increment of the adjacent typing is only 1, and in this case, the dilation is 2. As you can imagine, the dilation can be 3 or even higher. And there can be some very interesting properties when we consider the relation between dilated convolution and the original convolution, especially in the context of the current image classification network. Let's talk about how we can use dilated convolution to achieve our goals. Here is a cartoon illustration of how we can transform the image classification network into a dilated network, which will both preserve the convolution filters as well as the input resolution. So we have a two-layer network, and the first layer is just a normal convolution, while but the first layer has a strat 2, so that it's also downsample the input. And the second layer is a normal resolution. So let me say that again. The first layer is a convolution with strat 2, while the second layer is a normal convolution. Then, if we want to have a higher resolution of layer 1, it's actually very simple. We can just fill in the convolution, because of course this is convolution. All those connections all have the same value, same width, and same with those connections. We can just duplicate those widths, those filters, and densely apply them on the whole image. So as you can see now layer 1 has a higher resolution, and we do not change the original connections. And layer 2 naturally become a dilated convolution with dilation 2. And if we want to have higher resolution on the second layer, we can just fill in dilated convolution. And we can do exactly the same thing on a much deeper network. For example, here is a VG network. It has several levels, and each level has a group of convolutions followed by a pooling and a strat. So because of this pooling and strat, we are progressively downsample the input resolution and for image classification task. The first thing we can do here is we can remove the strat and the pooling as we described in the previous slide. So we can simply extend that 1D operation in this 2D convolution, and so that we can preserve the operation or preserve the resolution after level 3. You can see now we do not have strat, which means that we do not have downsampling. And then this we can call this a front-end network. So again, instead of doing upsampling and merge the layer from different levels, we can remove part of the operation and insert dilated convolution, so that we can just preserve the output resolution of level 3. And we can see the immediate results. So from FCN, you can see that we sometimes miss some structure of the input of the targeting objects, and may also miss some areas, and also get a very coarse boundaries. But with our front end or with our dilated network, we get a much cleaner boundaries of the objects, and also we can recover the same parts or finer structure of the objects in the image. Here are some more illustrations. So for example, in this image, not only that we want to segment the horse and the person, we also want to segment the cars which are in the background. You can see that with FCN, we get very blurred boundaries, but with our front end, we get much sharper segmentation for the horse. And at the same time, without additional processing, we can get the objects in the background as well. And it is the same for this image, where we can get much sharper boundaries for the target, for the airplane in the image. Now let's talk about another thing. or another key task in semantic segmentation, which is context. So context actually have multiple meanings in segmentation. The first context is the context between objects. So here is an illustration. If we want to classify this pixel as a pixel on a pedestrian, then we need to know that not only this pixel looks like a person, we also need to know it's actually this person is walking on the road. Similarly, if we want to know that this person, or if we want to know that this pixel is on a rider, and we must know that this person that this pixel belongs to is on a bike, so that we can correctly classify this person as a rider and also assign a correct label to the pixels on this person. And there are another kind of context is context within the object. So it's very similar to the context between objects. For example, if we want to classify that this is a call leg, then we must know that it belongs to an object with a call head. And similarly, if we want to classify this as horse leg, even though it's very similar to a call leg, we know that it's connected to a horse head, so that we know, okay, this pixel belongs to a horse instead of a cow. And but how is our network dealing with context? And is there any deficiency here? So we actually realized that when we dilate the VGG network, even though it's very deep network, when we want to look at this pixel, VGG network can only give us this level of receptive field, or in other words, it can only see a context within this area. But for us, even if we want to classify this pixel as a dog tail correctly, because it's very similar to a cat tail, we need to look at the whole objects or a bigger context in order to classify that pixel correctly. And how big a receptive field we need? First of all, we know that we do not need to look outside the image. All the information about this image should be within this image. The second point is we also know our lower bound, which is it can be at the other end of the image. It means that the total receptive field of our network should probably cover the whole image, or at least the biggest size of the object. And how can we get a larger receptive field? There are mainly a couple of ways to do that. The first thing is we can stack convolutions. Each time when we stack a 3x3 convolution, we increase our receptive field by 2 pixels. And of course, that is a very inefficient use, or very inefficient way of increasing our receptive field. If we want to have a receptive field of 400 by 400, then we need hundreds layers of network, and all composed of 3x3 convolution. So another way is to save the 3x3 convolution or to amplify the receptive field, we can downsample the image. For example, for the same 3x3 convolution, if we downsample the image resolution by half, then we increase our receptive field by 2. So, but we know that those are bad ideas for segmentation, because if we stack stack convolution, we will have huge overhead of computation. And if we do downsampling, then we will lose spatial information. And here we can turn to dilated convolutions again to have bigger context. And this related to a second property of dilated convolution. It can actually increase the receptive field exponentially without downsample the input resolution. For example, here we are illustrating stacking three layers together, and for each layer we are increased dilation by 2. And here we are only illustrating the receptive field of one kernel or one convolution. As you can see here, on layer 1, the receptive field is in the shaded area, is 3 by 3 9 pixels. Please note that on this layer, no matter how big the dilation is, we will always have the same receptive field. However, the magic happens when we stack layers together with different dilations. So here on the layer 2, we have like dilation 2, and when we put it together with first layer, you can see that we can get a contiguous region of receptive field, and then this receptive field also increase accordingly with this dilation factor. And again, on dilation on layer 3, even if we increase the dilation again and multiply it by 2, we are extend this reset field by a factor of 2 as well. So to quickly have a large context, we can actually do this exactly with multiple levels of layers with exponentially increased dilation. And you can see here our receptive field also increased significantly together with the increase of dilation. And we find that this context module can effectively avoid some issues due to lack of context. For example, in this for this dog, the origin if we only use the front end, the receptive field cannot cover the head of the dog, so that when we segment the tail part, we do not know whether the tail belongs to a cat or a dog. It's very hard to tell. Therefore, and actually the network, based on some dataset bias, try to classify this part as a part of a cat. And when we apply the context module, we can segment the whole objects coherently and avoid those errors due to lack of context. And it's the same for this animal and also for this bird. You can see that originally this part of the bird is wrongly segmented, but with the context module, we get much more consistent segmentation for the whole object. And we just find that this scheme can consistently improve our original segmentation. It turns out that this ability of aggregating large context quickly is also useful for audio analysis. This is the work released by Google DeepMind, which achieved breakthrough performance on audio synthesis. And as you can see here, they apply dilated convolution on one dimension, and so that they can consider a long period of audio piece in order to synthesize a new sound. And of course, because of the importance, context has also been studied in a lot of other works. And here is another example called pyramid scheme parsing network. And they use so after we extract the feature map from the basic network, they use different size of convolution to reaggregate the information from different level again, and then concatenate them all together at here. So far, we have resolved the question that if we want to design a network for semantic segmentation directly, what we want to do and how we can leverage the filter learn from image classification. And what if we want to do the other way? That is, can we use semantic segmentation network to do image classification? And the technical question behind this is, does high resolution feature map can benefit the classification task? So if we preserve the space resolution even at a high level, will it also help the classification to pick up the small details on the image? And fortunately, to study that, we can also use dilated convolution. So here is another view of how we can transform a ResNet 18 to a higher resolution feature map with dilated convolution. So as you can see here, so the ResNet 18 also follow the scheme of VGG with multiple groups. Each group has downsample the resolution of the previous feature map, and then create a deeper representation, and we can replace those downsampling with dilated convolution, so that we can have the same connections with the original network, but only the higher resolution feature map at each level. Here I want to mention one details about the residual networks, and it's also applied to a lot of other network design. So even though that the residual network progressively downsample the image, and usually it does not downsample it directly to a one by one filter. It will downsample it by 32 times, which by ratio of 32, which means that it will downsample 5 times, and then the resolution will be very low. And then at this low resolution, we can directly apply a global pooling on top of the feature map. Usually the feature map is 7 by 7, and then we can do average pooling from those from that activation map of that 7 by 7, and then get a one-dimensional signal by pulling from each individual channel. And using this one-dimensional signal, we can do a KV classification. And using even if we have a higher resolution feature map, we can still do the same. In the original ResNet, the HNW is 7 by 7, and if we if we remove some of the downsampling in the earlier stage of the network, then the feature map can be 14 by 14 or even 28 by 28, so that we will be able to see a higher resolution feature map. At the same time, we can still do a classification by using this global pooling. And another interesting property of this is if so here is the feature activation, and this one is the classification network that will classify this C channel one-dimensional signal. And if we remove the global pooling and directly apply this classification at each location on this feature map, then we will be able to get a class activation at each location of the this feature map. So to illustrate that further, you can see that here this is ResNet 50 by removing the global pooling, and we are observing the class activation for this target object. For example, in this case, we are classify each pixel and extract the class response of cat. And you can see that the ResNet 50 can give us some class activation, even though that the resolution is very low here. On the other hand, if we use dilated residual network, which will only downsample the image by a ratio of 8, then we can see a much detailed class response at each location of the feature map, and it can be directly correspond back to the original image. And this is the same for the other image. You can see that um, for example, for this animal, we are getting a rough idea about the boundary of the animal. This is very interesting because when we train those network, we only have image level label. We do not have information about the object location. As you can see here, the network can automatically learn that which pixel correspond to the targeting objects. And this is part of the scheme of semi-supervised learning. Basically, we have, or this is part of the scheme of weakly supervised learning. Basically, we have a weaker label here, the label of the whole image instead of label for each pixel. But we can predict the label for each pixel instead after training the whole model. And we also find that just by increasing the resolution of the feature map, we can directly get much better performance. For example, if we use ResNet 18 and dilate it with our scheme, and we can improve more than 2-point accuracy on ImageNet classification, and the trend is the same for all the other networks. And remember that between these two networks, we have same number of parameters, same number of channels in each layer, and also same number of layers. The only difference is the output resolution of each layer. And you can see that if we can have high resolution feature map, we can indeed improve the classification accuracy of the whole network. And as you have already seen, the network can also give us some location information about the targeting objects just from the class activation map. And we can use something very simple methods. Say we put a bounding box like this blue box on top of those class activation, and you can see that we can locate the objects like approximately. And this is for a lot of objects, this is very accurate. And at the same time, we also have some shortcomings for this method. So if there are multiple objects in the image, then our network cannot tell how many objects there are from the class activation. And even further, we can use this class activation as a signal for segmentation. So here we can combine this class activation with grab cut, a way of extracting foreground, and then to find the segmentation of the targeting objects. For example, in this case, the target is the roof, and for this case is the dog. However, when we look further into those class activation, we realize that there are a lot of editing grading artifacts on the class activation when we have higher resolution feature map. And as you can see here, there is a clear repetitive pattern on this image, and on other classification it's the same case. We see that the class activation for these objects is not continuous. Sometimes it's very strong, sometimes it's very weak. Let's try to understand how this happened. So first, we can dive into the class activation for each level. Each level consists of several residual blocks. As you can see here, for the initial level, it's doing low frequency, high frequency separation, and for the second level, it looks like it's doing edge detection. And at a higher level, they more and more high-level features are extracted from the images. And this actually brings us one interesting observation. The network is actually not only doing like integration. The filters are also doing differentiation in order to produce those high frequency signals. And why that can be a problem? So let's see that the first let's see what happens when we have a discontinuation on the class activation. This will be a natural result of differentiation. Usually differentiation is intended to give us some discontinuous signal that tell us that where are the say edges or corners are. And then when we have this one bright spot on the whole feature map, and then we do a dilated convolution with dilation 2. And you can see here that this single spot will produce a checkerboard artifacts here. And this is very similar to what we observe on the final class activation. And to resolve this problem, we change the network at several parts. First of all, at the initial stage of the network, we are trying to reduce the artifacts and reduce the discontinuation of the signals by removing this pooling and threading, and replace it with several levels of convolution blocks. Those convolution blocks will gradually downsample the image while reducing the artifacts. And you can see here, this is how it works. So if we are using the original pooling and thread method from the input image directly, we get discontinuous signal like this with a lot of noise. And if we do this gradual convolution and downsampling, we get much smoother signals from the original image at a lower level of the network. The second thing we can do on the original network to reduce the grading artifacts is adding more convolution layers at the end of the network without the dilation, or with decreasing dilation, with decreasing amount of dilation. So you can see here, at the final stage our dilation is 4, and then we gradually decrease the dilation to 2 and 1. This is very similar to the ideas in super-resolution, where you will use a small kernel Gaussian filter to filter the final image to remove some artifacts. And here are the comparison of the class activations. So you can see this is again original class activation of the ResNet, and then this is ResNet, the naively dilated residual networks. So with our change, you can see that we can get much smoother class activation, and even for this lizard, we can even detect the occlusion from the class activation. And here, those two small animals can be separated in our final class activation. And of course, this better class activation map also leads to better segmentation performance, as you can see here. And this artifact actually has been observed in a lot of previous networks as well. So the ideas here can also be applied broadly in the other methods. And here, this on semantic segmentation, you can see that with DRNA50, like 50 layer dilated residual networks, it will produce this type of artifacts in the network. This mainly happens when the network is uncertain about the class categories. But for our for DRNC26, even though it's shallower, but it has similar performance, and you can see that it doesn't make those grading artifacts on the predictions. And this high resolution class activation map can also be broadly used in the other area as well. So for example, here we also use it on makeup transfer, and this high fidelity class activation can also produce realistic fixed synthesis. And in this work, the main driver here is you can use dilated convolution to do a style transfer between a source image and the makeup image to synthesize new makeup on the face. And also the dilated convolution has also been used in other area like dilated residual networks for image denoising. So even though dilated convolution has become a major method in building segmentation network and become the key components for high performance segmentation network, skip connection still have its position in building efficient networks, and because it's usually if we do not need to keep the high resolution feature maps, then we can reduce some of the computation. And then the question here is, can we merge these two things together? That is, we can both have very effective segmentation network at the same time use skip connection to reduce the computation. And if we look at the previous work on the on using skip connection for layer aggregation, it generally follow this trend. We have several building blocks, several levels of networks to extract the deeper representation from the input image, and then in the end we iteratively aggregate the building blocks and outputs of the layers together so that we can have both semantic information and spatial information at the output. And in this simple figure, which generalizes the previous work, you can see that for the lowest level, even though that it has the weakest semantic meaning, but it's connected to the output layer with a shallow network, sometimes even just one layer of convolution. So this may become the bottleneck for having very semantic spatial information. And if there's anything we have learned during the past 10 years, it is we need deep network to extract good representation, and even if the goal is to extract semantic information for each individual pixel. So we need deep network for layer aggregation, but how we can achieve that? So first of all, let's look at the general building blocks. As you can see here, no matter how those networks has been involved in classification, they generally follow this structure. Like you can have input, you have input, and then the input information is passed into each building blocks. And the first thing we can try is, instead of passing the information linearly, sequentially into different convolution building blocks, we can also aggregate them together from level to level into this tree structure, so that the lowest level also have a fast pathway to the output, and the output can get a chance to learn how to combine information from different levels together. So here we can aggregate layer outputs from multiple levels, and at the same time we keep a flexibility of plug in different building blocks in the lower level black box. And we can actually make some change for that. So originally, the input for this building block is from the previous convolution block, but we know that like topologically, all those building blocks can be before this convolution block. And why don't we take this we call reentrant aggregation, which means that instead of taking the output from the previous convolution block, we take output from the previous whole subtree, and the same for this block as well. So then the input for this block will become more expressive just because it has already been aggregated from the previous layers, and the longest path is becoming deeper. And another thing we can do here is you can see for the final building blocks, it's already contain deep representation of the input image and the lower level layers. We do not need to do another deep aggregation of the final building blocks, and therefore we can remove the building block from the pathway and also here, so that we can have a faster aggregation from the higher level building blocks to the subtree. And another good thing about this is the overhead for the additional building blocks is only log of the total number of convolution blocks. Or in another way, the number of aggregation block is small compared to the number of convolution blocks at the backbone. Therefore, we introduce a minimum overhead to the overall network structure. And we can use this idea to reconnect the convolution blocks, say in the Arduino ResNet. And so as you can see here, we can keep the rough structure within each stage of the Arduino network. But with each network, instead of sequentially connect the building blocks together, we are using our hierarchical aggregation to connect the building blocks. And it turns out that this new overall structure can give us better balance of prediction errors and the parameters. Here, this is the curve for different variation of ResNet. So basically, when you have more parameters, we will have lower test error. And for DLA, so we use the exact same building block, same convolution block with ResNet, and only change the exterior structure of the network, and then we can get a better trade-off between accuracy and the parameters. So this is the common curve we use to study the different design of the model, and to show that some design of the network can achieve better balance between parameters and accuracy. And here is another another work, and this is the trade-off for the ResNext. And when we plus the ResNext block into our network module, we can get even better balance between accuracy and parameters. And we have a similar story for computation, which is measured by how many multi-add we have in the network. So it turns out that this structure can also be useful to design very small models. For example, here we have some small model with many layers, but within each layer there are much fewer parameters. Overall, say in those networks there are about around like 1 billion number of multiplication and addition. And those models are all like around 5 megabytes if we want to store them in the memory or on storage. And we can also achieve a good computation or trade-off while we are getting lower errors. So here is another problem we commonly consider in fine-grained in classification. It's called fine-grained classification. In this task, instead of classifying whether the image contains, say, a dog or cat, it considers subcategories of those general objects we see. For example, in this task, the goal is to classify different types of airplanes. And you can see that without the additional change of the structure, the DLA network, deep layer aggregation network, can achieve much better accuracy than the previous models that it designed specifically for this fine-grained classification. And this shows that the deep layer aggregation can indeed pick up the spatial information and the small detail difference in the original image, even though that the task is classification. And the same trend is true on the other datasets as well. For example, we have datasets to classify different breeds of birds, different type of cars, different type of airplane, and different type of food. And speaking of dense prediction, which we were considering, so we talk about that in the current dense prediction network, the low-level information has been shallowly aggregated to the output. And we can use the same idea of deep aggregation. Instead of aggregating the information from top to bottom, we can actually aggregate information from bottom to top. And we can here is a diagram that how we can use this iterative aggregation in the segmentation, in performing segmentation task. Here we again, so those black box are different levels of original classification network, and the number means the ratio of the downsampling each ratios. And you can see here each green box represent an iterative deep aggregation, and we repeatedly use this iterative deep aggregation until we get the desired output. Here the output is it's a downsample of the input image by ratio of 2. And with this combination of hierarchical deep aggregation and iterative aggregation, we can observe that we can get a better performance than the network using shallow aggregation, and it can achieve performance similar to the deep dilated residual networks. At the same time, because we do not need to keep high resolution feature map at the higher levels, and we can save a lot of computation. We can save the model itself become much smaller than the deep dilated residual networks. And here are some more visualizations. So you can see here that this is an image from Cityscape, and this is the segmentation output from using deep layer aggregation network. And if we look at some objects far away, you can see that even for the background building, it can segment clearly. And even for some foreground small objects, the network can still find the boundary of objects very accurately. And overall, the network can segment the image with very good accuracy. And it can also achieve very good accuracy on the boundary task. So it just shows that with this deep layer aggregation, we can get a very good balance between low-level details and high-level semantic information, so that it can perform multiple tasks, including classification, fine-grained classification, segmentation, and even boundary prediction.